Today we're going to be looking a little bit more at what happens as populations grow and what can determine how much a population is allowed to grow. So when a population grows, it all depends on what we call limiting factors and a carrying capacity. And we're going to look at both of those words in detail over the next few slides, but they are very important to know. So your limiting factor are going to be, and you could kind of figure this out by looking at the name, but factors or things that limit the population growth. Carrying capacity is just talking about the max amount you can have. So carrying capacity is just saying how many individuals there can be in that environment. So let's go ahead and look at each of those words. So limiting factors are going to limit how much the population can grow. So I want you to think about it for a second. What are some things that would determine or limit how much a population would be able to grow? Well, some examples are going to be food, water, and space. People talk about how goldfish will grow only to about the size of whatever tank you put them in. And I don't know exactly the details of that, but that's just an example you always hear. So the amount of space that this goldfish has is going to determine how much he can grow. The amount of space I have available in my room determines the population of students I'm allowed to have. If my room can only hold 16 students, then the max amount of people I can fit is 16 people. And so space limited how many students were allowed to come to my room. Another one is going to be water, and this also goes for food. If there's only enough water in this population to support 8 elephants, then the max population size I can have is 8, because the rest of them would end up dying because they would not, or leaving, because they would not have enough water in order to survive. So when you're looking at your limiting factors, you're going to look at the food or the water competition, the space you have, the disease that's around, the predators, all of that. They limit the amount that the population can grow. Notice, limiting factors are things that limit growth. None of them here are numbers. So whenever we refer to limiting factors, we are not talking about the number of individuals. We are talking about what thing is limiting that number of individuals. So limiting factors create a carrying capacity. And make sure you write this down. That's going to be a very important thing to know. And carrying capacity here is represented by a capital K. And you'll end up seeing that in graphs. So limiting factors, those things we talked about, determine or create that carrying capacity, that max amount that's allowed. So the carrying capacity is the max population size that can be supported in an area without destroying that habitat. So if you have water, so we'll say we have enough water that it can only support 8 elephants, then 8 is the carrying capacity. Water is the limiting factor. So water is the thing that created that carrying capacity of 8. If I only have enough space for 16 students, that example I used earlier, space was the limiting factor. 16 was the carrying capacity. So that's the max amount that I could have. When you have a carrying capacity, this is what it looks like on your graph. So you're going to see a lot of graphs when we talk about populations. So it grows very, very quickly, and then as soon as those limiting factors come into play, that's when that carrying capacity hits. So your carrying capacity is represented by that flat line because it can't go above it, and populations always grow to the max size. It's just a pattern that you see in nature. Technically, your carrying capacity is actually a squiggly line. It's not straight across. Because what happens, let's talk about the elephants. We only have enough water. That's going to be the limiting factor we're going to go back to. So we only have enough water for 8 elephants. So 8 would be that number up here for the carrying capacity. So what happens is nature's going to go up and it's going to hit that max that it can. And it's actually going to go just a little bit over. So say there's about 10 elephants born. Well, not all of them can survive, so they're either going to end up dying or they're going to have to leave. So then the population drops back down. Well, as soon as it drops back down, more individuals are born. So it goes right back up, and then it goes right back down and right back up. So every time you end up having just a couple more individuals than what that carrying capacity can hold. So they end up going back down because you can't have more than the carrying capacity because there's not enough resources for all of the individuals to survive. But as soon as it drops, then more are born, and then they go back down, and then it goes back up and goes back down. So technically, it is a little bit of a curvy line that you see. When we do the line going straight across, that's our line of best fit. But you see how it grows exponentially, and as soon as the limiting factor set in, all the growth evens out. So this growth rate would be equal to 0 because it's not getting any higher. As soon as people are born, the death rate kicks back in. So we would say the carrying capacity has a growth rate of 0 individuals in that area. So what goes up must come back down. If you exceed, meaning if you go past that carrying capacity, then the population will drop. So if you exceed, if you go past / if you go over the carrying capacity, then the population will drop back down. That's why the carrying capacity is technically a little bit of a squiggly line. You cannot go higher than the carrying capacity is and all of the individuals be able to survive. There is a carrying capacity always in nature. Nothing can keep growing rapidly forever. Limiting factors always kick in, and they always end up limiting that growth to create that carrying capacity. So here I have 5 slices of pumpkin pie. Or actually, let's say it's sweet potato pie. I like sweet potato more than pumpkin. Well, what would be my limiting factor? And then what is my carrying capacity? So I want you to think about that, and I want you to actually answer this question so you can see if you're getting this right. So what is my limiting factor? And then what's my carrying capacity? Well, my limiting factor is the number of pie slices. So number of pie slices, or you could say the amount of pie that you have. My carrying capacity is 5 because that's the maximum amount I can support. Remember, the limiting factor is always the thing that is stopping your growth. The carrying capacity is always the number of what the growth can be. So when organisms have limiting factors, they show what we call logistic growth. And I want you to make sure that you know logistic growth well, because this is another vocab word. Logistic growth is something that is logical. It makes sense. When there's no limiting factors, you have what we call exponential growth. And the other thing I want you to do is to draw these graphs. So this one over here, this is your exponential growth. So make sure you draw that. And this one over here, this is your logistic growth. Oops. So just draw a short little graph and label it for exponential and label it for your logistic. So logistic has a carrying capacity because that makes sense. Logically, nothing can grow forever. If every species showed exponential growth and it just shot up and never came back down, it just kept growing and growing and growing and growing, then that would take over the world. And nothing's going to be able to do that. So everything goes up and it grows exponentially at first. And then at some point, it hits those limiting factors, creating that carrying capacity. And that's why this is called your logistic growth. So we're going to move on to the next slide, and I'm going to show you 2 nicknames that these growth curves have that you have to know. The first one is your exponential growth is also called J growth. So make sure you know that. And so if I was going to write out somebody's name, we'll write John, then this J looks like it's that exponential growth. It goes and then rapidly shoots up, and it would just keep going and going and going and going. So they call this your exponential growth, and or your J growth for exponential, and you can kind of see how that looks like the J. Bacteria often shows J growth because of how rapidly it grows. Your logistic growth, Again, this is when your limiting factors kick in. This is called your S-shaped growth. And so when you have your logistic growth, you can kind of think about if I have messy handwriting, I was writing out Smith. It kind of sort of looks like an S. So it goes exponential at first. It always starts out exponential because nature always does that. It always tries to hit the max of everything. And so it starts out exponential, and then when those limiting factors come in, it hits that carrying capacity. All J-shaped growth turns into logistic growth at some point. It's just a question of when. Unfortunately, since we are not here, we won't be able to play this game. But this leads us to what we call predator-prey cycles. And make sure you jot this down. You can write down predator-prey and then write down kind of the explanation that we talk about. But with your predator-prey cycles, when you're looking at predator-prey relationships such as a fox and a rabbit or a wolf and a deer, your predators and prey are going to limit the size that each other can be. So, for example, you have this rabbit population, and as the rabbit population shoots up, your predators are going to have more food to eat. So they're going to start growing because they're eating all the rabbits. But notice when it gets all the way up here and your fox population is growing so much, they have now eaten all of the rabbits. So your rabbit population's shooting back down because all the foxes are going to eat the rabbits. And so now there's no more rabbits for your foxes. So your fox are going to end up dying and their population will drop. Well, with the fox population down, your rabbit population is able to shoot back up. And now that the rabbit population's back up, your fox population will have more food, so they're going to grow as well. And again, same thing. Once the fox population gets so big, they're going to be eating all of the rabbits, so the rabbits are going to have a massive drop in population, which means that the foxes are going to have less food, so they're going to have a massive drop in population. Now that they're down, the rabbit population will have time to grow back up. As they grow up, the fox population will have time to grow back. And this will happen again and again and again. It is the same cycle that we see in the same cycle we see in wolf and deer. Every type of predator prey you see, the prey grows drastically, causing the predators to end up growing. But once all of the predators are eating the prey drops, which causes the predator to also drop. And so you get this up, down, up, down, up, down growth. So the predator is going to limit how many prey I have, and then the amount of prey I have will therefore limit the amount of predator that I can have. So they keep each other in kind of a checks and balance system, preventing one from being able to take over that particular ecosystem. And that's what we call boom and bust. So you have the population boom up and then it busts down, and it boom up and then it busts down, and it booms up and then it busts down. And that has to do with that predator prey. As one goes up, the other goes down, and so on and so on and so on. This all brings us to human population. We have talked about all the different types of populations, the types of growth that they show, and the things that affect their growth. Which brings us to the question, well, what type of growth do humans have? Humans are currently showing a J growth curve. So if we have J growth, that means we have exponential growth. So we are shooting up in our population. Nothing can grow exponentially forever. So we are currently growing at a rate of about 80 million a year. And so the question is, why have environmental resistance, aka limiting factors, not taken effect? Well, we have been able to escape some limiting factors that would have been able to limit our population earlier on. Some of those examples would be we can alter our environment. So when it comes to being able to get water, well, we don't have to depend on a watering hole. We can actually drill down into the ground and get our water. When it comes to technology, look at all the technology plus the medicine we have that can get us to live longer lives, that can allow us to have children It used to be a very risky thing when you gave birth. It was risky for the mom and the baby. Many didn't survive. That's nothing like it is now. Now pretty much all of them survive due to our technology and our medical revolution. And then agriculture revolution. This was a very big deal. Food is a big limiting factor. Well, we have been able to grow food year round. Think about it. In the middle of winter, you can still buy strawberries. And that goes back to our agriculture revolution. You never have to wonder, does the grocery store have food this month? The grocery store always has food. We always have food available to us. So we've been able to get around a lot of limiting factors, but nothing can grow exponentially forever. So at some point, that will kick in. And this is just showing you the growth that we have. A lot of people think that what will end up kicking in for us and cause us to start hitting that carrying capacity will be when we hit the limiting factor of space. There's only so much space on the earth. The population is growing rapidly. We're going to run out of room. And it's not just for where we can fit people, but you have to have space to have food, to grow all of our food. You have to have space to put all of our waste. When we look at landfills and things like that, where's all the waste going? If you start running out of space and these two things start mixing, you're going to have disease start going up. You're going to have famines that go up, all that type of stuff. We look at because the population growth all depends on, or the carrying capacity, it depends on how many individuals you can fit without harming the environment. Well, you now have global warming that's causing a lot of harmful things. So is the population getting so large to a point that it is causing an issue within the environment? And yes, we do see that. So some people, and this is not sound like doomsday, it's not like a movie where tomorrow all these people are just going to end up dying. That's not going to be the case whatsoever. But we have to look at how are we managing the resources that we have, so that you can prevent a carrying capacity from coming into place as long as possible. So for example, when we look at our waste, well, can we start recycling more? Because if you recycle more, then you make the waste problem go down, you make the disease problem go down, and you now have more space for food. So something as simple as doing more recycling gets rid of a lot of this doomsday stuff that people have in place. Or people think about how bad global warming is getting and all the issues that it can cause. Well, yes, but there's a lot of things that we can do to limit those effects and make those effects go down, therefore putting off a carrying capacity further and further and further down the road. So this all goes back into how are we being responsible for the space we have? How are we managing our resources in a wise manner? Because that's what we have to start thinking. Think about with water. There is going to be a day zero or water scarcity where there's not quite enough water for everybody because of our population being so big. Well, we have to start thinking, how are we going to stop wasting water so we don't have that issue? And that, again, don't think doomsday. Just think that you have to start turning the faucet off when you brush your teeth and start doing shorter showers to help prevent some of those issues from coming up. So think about that. Think about how you can be wise. There is another video that shows you the human population growth and talks a little bit about using those resources wisely. So once you end this video, go back and watch that one. It will be in that Canvas page. And then that was the end of this unit. So the next thing we'll have to do is our study guide and then our test. So again, let me know if you have any questions about anything.